Let's do another related rates example. This example is in some ways, I think, rather more straightforward than the example we just did. A hot air balloon is rising straight up from a level field, and it's being tracked by a rangefinder 500 feet from its liftoff point. At the moment that the rangefinder's angle of elevation is pi divided by 4, it's increasing. I mean, the angle of elevation is increasing at a rate of 0.14 radians per minute. And we'd like to know how fast the balloon is rising at that moment. We'll start with a picture. We've got a liftoff point, and we've got a rangefinder, and we've got this balloon rising up. And we're told that this distance is 500 feet, and we're given information about the angle of elevation, so we'd better sketch that in. Now, it's very important to keep track of what is a constant and what isn't. The balloon is rising. As the balloon rises, of course, the angle of elevation changes. So it's true that ultimately we are interested in a specific angle of elevation, pi over 4 radians, but the fact that we're ultimately going to ask what happens here shouldn't make us lose sight of the fact that the angle of elevation is a function with respect to time. Contrast that with the distance between the rangefinder and the takeoff point. The rangefinder is stationary. This distance is genuinely fixed. And we're asking a question about the height of the balloon. So let's label that as well. And now we can ask, what numbers do we have? And let's explicitly make this point, reiterate it. We won't plug those in until the end. So we're told what's happening when the angle is pi divided by 4. So let's write that down. And we're told how the angle is changing at that moment. It's increasing at a rate of 0.14. But as I say, we're not going to plug these numbers into anything until the end of the problem. For now, the balloon is rising. This angle is a variable that's changing with time. It would be a mistake to look at this equality and treat the angle as a constant. What do we want? We want to know how the height is changing. That is, the derivative of the height when theta equals pi divided by 4. Can we relate what we want with what we have? Can we relate the height that we want information about to the angle that we have information about, especially bearing in mind that we also have information about this side of the triangle? Well, if we want to relate an angle, an opposite side, and an adjacent side, I suppose, properly speaking, there are two ways we could do this, but probably most of us would rather work with the tangent over the cotangent. And now we'll differentiate. And I know I'm sometimes a little inconsistent about when I use function notation and when I don't. I used function notation here to emphasize the very important point. We're going to differentiate with respect to t. So what we have here, we have a tangent. The derivative of a tangent is secant squared, but we don't have the tangent of t. We have the tangent of a function of t. The chain rule gives us this. The derivative of the outside function with the inside function stuck inside it times the derivative of the inside function. Here, this constant just sticks around. The derivative of h is We don't know what the derivative of h is. That's precisely what we want to find out. And now we can substitute in the stuff that we have. The secant squared of pi divided by 4 times 0.14 times 500 equals h prime of t. This problem's copied from the textbook. I assume the idea the author had was that we'd evaluate this mentally. Pi over 4 is one of our standard angles. But what's the point of doing that? You're going to then have to go to your calculator to do this multiplication and get the decimal approximation. I'm going to just plug this into my calculator. Your calculator will not have a secant button. It might be hiding somewhere in a menu, but it will have a cosine button, and the secant is 1 divided by the cosine. Plug this in. We actually do end up with a very clean number. That's how you can tell that it's a problem from the textbook instead of real life. The hot air balloon is rising at a rate of 140 feet per minute.